And also do let us know when you start streaming. All right. Hi all. Welcome to the session 6 of the AI Summer School program. So we'll be starting shortly. We'll be starting at 5 p.m. There are still 5 more minutes. So today's session will be mainly about optimizers and also data pre-processing techniques. So if you recall, in the last session, we have introduced all of you to the world of deep learning and we have discussed about neural networks, gradient descent, etc. So today we'll be learning about some more tools, some more add-ons to these neural networks, which will definitely improve your model performance and enhance their performance. So do inform your friends as well if they haven't joined yet. We'll be starting at 5 p.m. And also regarding the attendance, I guess by now it must be clear, but I'll just repeat myself again. So we'll be showing the attendance QR in between the sessions. So we'll be showing the QR 2 to 3 times so that even if you miss scanning the QR once, you can scan it again later. And we'll not be sharing the attendance links on the WhatsApp groups or also on the YouTube chat, just to ensure that the people who are attending the session only can scan the QR and get access to it. And all the content for today's session, it has already been uploaded on the GitHub page. So do check that out. And also the content for all the previous sessions, the YouTube recordings, everything will be available on our GitHub page and also on our YouTube channel. So you can check the playlist. I guess that's all. We'll be waiting for another 2 to 3 minutes and then we'll start off with today's session. And also regarding the task, I guess till now we have given you only one task. We'll be uploading another task soon. So throughout this program, we'll be having 3 tasks which you should be attempting. And we urge you all to attempt the test because the task or the test and also the quizzes that we are sharing, because they not only help you, they will be definitely helping you to revise the concepts that were discussed in the session. And also, if you are low on your attendance or if you have missed more than 2 sessions, you can consider these assignments and the tasks to be a compensation for that. So yeah, definitely do attempt the tasks. They'll be providing you with a much more better understanding and hands-on experience, and you'll be implementing whatever you have learned in the session. So that will make your concepts much more clear. Yeah, that's all I have to say. We'll be waiting for another 2 3 minutes and we'll be beginning shortly. So Gandhar and Rajiv will be the instructors for today's session. We'll wait for 2 more minutes. And if you have any doubts, you can raise your hands during the session, throughout the session. Okay. And we'll be giving you mic access so that you can unmute and speak. Adding to that, we have also shared the Slido Q&A link on all the WhatsApp groups. We'll be sharing it even on the YouTube live stream. Okay. So what you can do is you can click on the link. You'll be redirected to a Q&A page where you can post your doubts, which will be taken up by our coordinators during the session. As people are joining, we'll wait for 2 more minutes. And also another piece of advice which I would like to give for all the beginners with this domain is not to get intimidated by the code or with the mathematics part, because even if you have attended the last session, you might have seen how using deep learning frameworks like PyTorch makes your life much more easier. If you have to code everything from scratch using NumPy, that requires you to have a very strong understanding of linear algebra and other mathematical topics. But deep learning frameworks like PyTorch, you also have scikit-learn. These make your life much more easier because you need not understand exactly what is happening behind the scenes. You should be understanding where to use which model, and also you should be knowing what all hyperparameters are there that you can tune. And that is the main reason why we are trying to emphasize more on the intuition part in all these sessions more than on the mathematics part. And definitely for the people who are not having mathematics background, we urge you to have look at some towards data science articles on linear algebra, etc. And you can definitely ask doubts on the WhatsApp groups as well. But to begin with, I guess a good start would be to have a, strong command over Python coding, and also having an ease of going through the documentation of PyTorch, documentation of scikit-learn. Because when you're using these ML or DL tools in the real world for solving real life problems, more than understanding the math, it is about how we implement them. So understanding and getting a better hold of these tools will make it easier than emphasizing too much on the math part. And definitely there are various Kaggle contests that you can participate in to understand these concepts better. And that is also one of the reasons why we are sharing some tasks with you so that you get a better hands-on experience. Saying that, I guess we have 130 attendees, so that's great. We can start right now. Rajiv.
So, hello and welcome everyone to the sixth session of this AI Club Summer School. So, in this session, we'll be covering optimizers and other tools to make your model work better. So, I will start with the presentation. So, what optimizers essentially does is it basically kind of reduces something called as the loss function so as to increase the robustness of your model. So, optimizers in general, it's a topic that applies to uh, every domain of ML and AI. It's not really a topic that's restricted to a specific domain. So this topic is kind of important for everyone to learn. So we'll start off with the optimizers topic. So the first thing that comes to mind about optimizers is something called as the loss function. So although this has been covered in previous lessons, I will be giving a general recap of the loss function. What the loss function essentially does is it is a quantitative representation of the error in your model. So what do I mean by error in your model? We know that AI Club or AI, it it tries to predict how well sample, or it kind of tries to predict a quantitative representation of the output of a particular sample. So when you try to predict something, there tends to be error in the actual value of what you are supposed to predict and what you actually predicted. So that this error is represented in the loss function. So the higher the error, the more your loss function will be. So we use optimizers to minimize this loss function. So one such example of loss function is called your mean squared error. What, as the name suggests, you have a square term. So what do we mean by mean? So you can see this expression I'm encircling with my cursor here. So this is your mean squared error. So it has a square, and your y cap is y predicted, and your y is the actual value of y at that value of samples input. So this graph kind of represents what we actually predicted. What we predicted is your fitted line over here. So you can see this red color line. So the each value of y in this expression basically comes from this line, and your y actual is basically your actual value of I. So that is represented by your blue dots. So when we compute this error, we'll get a quantitative representation of how the value will be as a whole. So what we try to do is we try to reduce this loss function so as to improve our model's performance. So what an optimizer is in layman terms is just an algorithm that tries to adjust the weights and biases. So I'm assuming everyone here has some kind of understanding of weights and bias from previous lessons of the AI Club summer school. So what we try to do is we just try to change the weights and bias in such a way that it minimizes the loss function. So now we have a question here. So for this question, I will be enabling my Slido link so all of you can answer. So I will just go to my Slido page right now. So I hope after I enable the link, all of you will uh, answer the question. So it's going to present. So I hope you guys have, yeah. So I have the QR is shown and you can also join using the link or you can join using this number. So I hope you guys will
So I hope everything is
kind of
clear in this.
see.
Do you now
know
observe
what I
that?
told you guys what a mean squared error is, so you guys can start answering. The QR code is here, and we have some responses. So I will wait for around 1 more minute.
Yeah, people, you can see the QR code on the left, right? So you can scan that QR code. People who are attending on mobile and who are finding it difficult, what you can do is go to slido.com and then you can directly type in this code that is being presented on the screen. They can give them some more time, let more people attempt, and then we can discuss. Yeah,
I'll be waiting for like 1 more minute or say 45 more seconds, so more people will end up answering my question. So I think that should be enough time. So I'll just kind of show the results now. So okay, people are still answering. So the correct answer is your A option. So I will explain why that is the case after I go back to my slide. But for now, this is the correct answer. So those of you who got it right, well done. And those of you who got it wrong, we can still learn a lot in this lesson. So so I'll be deactivating this poll. So why is that the case that mean squared error ends up having a always has a minima? So as you can see from the expression clearly, this is the expression for mean squared error. And what is the degree of this polynomial? You can see at the RHS there is a square term for every term. So you have you basically have a polynomial of degree 2. So and the sign is basically positive. So we'll end up having a convex function which ends up having a minima. So this is the reason. So those of you who got it right, well and good, and we can learn a lot in this lesson. So we'll move on. So this is basically the plotted form of the loss function. As you can see, I'm basically representing using two variables here, your theta1 and your theta naught. Why I'm using only two variables? Because the third variable is basically a function of your two variables, or it's not a variable. The loss function is a function of two variables, and it's easy to represent in a 3D plane or a 3D domain here. So here you can see how it's represented. So what do we want to reach is the minima, as explained a few minutes back. So we want to reach the minima and improve the robustness of our model. Now we have gradient descent. Although this has been covered uh, in previous lessons, I will just recap it here because most of my lesson is based on this gradient descent, and we'll basically use this gradient descent and tweak some parts of the gradient descent formula to have more robust optimizers. So for those of you who attended the previous lesson for gradient descent, we'll have a good recap over here. And for those of you who didn't, I'll be teaching it in good detail. So what gradient descent basically does is you place your variable. By variable, I mean your weight or your bias. So one thing I want to add is why are we like the when we say optimizer, we basically try to change our weight or bias in such a way that it reaches the local minima that affects our loss function. So this is our variable's starting point. So as you can see this black dot here. So this variable is your weight or your bias, which you want to tweak using the optimizer so as to gain a minimum loss function. So it will compute the gradient at that point, and all it does is move opposite to the gradient. So that's pretty simple to understand. Imagine if you're on a hill, you basically kind of tend to fall down to the valley in between those hills. The valley is basically a place with zero gradient. So when we fall down, it basically means we are moving towards the minimum. So in this case, if your gradient is positive, the change of your variable will be negative. So that's basically gradient descent. So we'll be going behind the math and stuff in a few slides. So this is just a good representation of gradient descent. It'll help you visualize why this works and what it tries to do. So stuff like this is kind of good to help me visualize what I want to do. So next we'll be having another quick question here. So assuming you guys understood what exactly gradient descent can do, we'll be testing that understanding using this quick question. So I'll be going to my Slido right now. All right, so we have a question 2 here. So I hope you guys are going to answer this question. So what the question says is, does the starting point of where we place our variable, does it affect the convergence of gradient descent? So this is a pretty uh, good question to help you understand why we use other optimizers, because the reason other optimizers were invented because of the answer to this question. So I hope you guys will answer this. So I'll wait for 1 more minute. So if you can't scan the QR code, there's also a number link. You can just use it on your phone and quickly answer. So that's a nice way to, the Slido has been maintained. So you guys we'll be waiting for say few more seconds. All right. So if people are still answering, I'll probably just might as well wait for a few more seconds. All right. So I'll be showing the correct answer now. So yeah, for those of you who got it right, well and good. So the reason is because there's more than one minima that you can converge to. So I'll quickly show why that is the case. Yeah, so you can see in this slide here, if you place a starting point. So I'll let you grasp on this diagram for a few seconds. So let us say our starting point is somewhere, say over here where my cursor is. The gradient descent just moves opposite to the direction of gradient. So in this case, gradient is negative. Just keep going to a positive value or to a more positive value until it reaches the minima. So sure, well and good, we reach the global minima, which is what we want. So this is one value of convergence for our starting point. So let's choose another starting point. Say we choose it over here where my cursor is. So similarly, my gradient descent will compute its formula and kind of converge to keep going to a negative value until it reaches this point. Because at this point there will be no change. The reason there will be no change is because the gradient is zero in that point. So as you can see, for two different values of starting point, you basically reached a different converging points. So the reason being there are more minimas. So it depends on where you start, that on where you end. So this is a good question. So we basically say that the more and more we go towards the minima, the more and less the gradient becomes, and hence we have to iterate more in order to change the weight by an amount, because the gradient will be really less near the minima. So the change of the weight will also be really less. So this is just one point to take into. So this is our mathematical formula that represents the uh, gradient descent algorithm. So we have the weight. So I'll let you guys grasp onto this for a few seconds. So you guys have already seen this formula before, but uh, I'm just going through it. So you have your weight at any iteration is equal to weight before that iteration minus the learning rate into the gradient of the loss function at that point with respect to the weight. So that's just neatly represented in this formula. So LR is your learning rate, Fx is your output, or it's your loss function. So where X is basically any variable that you're considering at your time of computation. So this is your gradient descent formula. So this is just my photo where I tried to like explain why the change happens at a certain point. So you have the change in variable is basically minus times of learning rate into the gradient at that point. So it basically is equal to when your gradient increases, when your gradient is positive, the change will be negative and so on. So this is obviously a good pictorial representation. So I hope you guys understood gradient descent to a good fashion. So we'll be going ahead. So learning rate is another important parameter that kind of determines how your model is going to play out. So we saw learning rate over here 2 slides back. So how this is going to affect the iterations, I will just show you while explaining learning rate. So as you can see in the formula, we have learning rate is proportional. The change in variable is proportional to the learning rate at that particular point. So if the learning rate is too low, the change in variable will also be really low, and we have to compute a lot. That will lead to more computational power and resources needed in order to carry out this gradient descent. So, and what if the learning rate is too high? You'll end up looking something like this. You don't want that, right? I mean, you want to reach the global minima, not expand your loss function. So this will also cause drastic changes, and we don't want the loss function to expand basically. So we just need something that strikes the midway between these two, something that's just right. So we can kind of graph the loss function with respect to different learning rates. A very high learning rate, as shown in the previous slide, it will cause the loss function to just expand rapidly. So that is something that's not in our mind. Then we have a low learning rate. So as you can see, even after a large number of epochs, the low learning rate does not really converge the loss function as much as it can. So, and we end up performing more iterations too. So we don't want to, use many computational resources and stuff like that. So we just want a balance in between these two. So a good learning rate will help the loss function to reach its minimum properly. as you can see, a good learning rate has the lowest loss function and also has a good computational resource usage. So this is about learning rate. Next will be, so now we'll be starting the actual part of optimizers. So in gradient descent, it's divided into three major domains. So one one of which, like, the divisions are based on number of samples, and basically what scientists want to use is depending on their own data set and their own computational resources and uh, things that things that depend on them. So all these three are useful gradient descents. So we'll just be going over them. So before that, I will just kind of explain what an epoch is, because it's an important term when it comes to understanding optimizers and machine learning in general. So when I say one epoch, it means that the model has gone through every sample exactly once, every sample in the dataset exactly once. So when I say what is an iteration is basically your uh, how much how the lower your batch size, the more iterations it will take, because an iteration is always as per a batch. So you have a set of 1,000 samples, and if I say the batch size is say 500, you'll end up having two iterations, one for your batch one of 500 samples and one for your batch two of 500 samples again. So it basically means iterations per epoch is basically it's two. So that basically kind of uh, that's a way of looking at how iterations work. So I hope epoch is clear to everyone. So similarly, if you have batch size of 100, you need 10 iterations to cover one epoch. So I hope this is kindly clear. So batch gradient descent is basically uh, just having exactly one iteration per epoch. That means you basically just cover all the samples in the data set in just a single iteration. So an example of that can be the mean squared error, which I spoke to you about in the first few slides. You basically just kind of use one iteration and you just compute the mean squared error. So that's very simple. And batch gradient descent is the type of gradient descent I was using to explain the other factors, like in my previous slides. So this is a very uh, you know generic type of gradient descent, which is used to explain gradient descent to people who want to learn it. So this is like you know batch gradient descent, and there are many examples of this. So what is of our interest right now, in order to see about robust optimizers? By robust, I mean optimizers of more advanced, uh, of more newer creations, and which have a better performance. For that, we use this gradient descent called stochastic gradient descent. So what stochastic gradient descent is, it just looks at each sample at the time of consideration. So you just compute the gradient by looking at the samples one at a time. Unlike batch gradient descent, you basically have to you basically just keep on updating the weight every time you see a sample. So in batch gradient descent, I explained earlier that we update the weight exactly after one epoch. So after going through all the samples, we'll update the weights in batch gradient descent. But in stochastic gradient descent, we'll update the weights after every sample. So this is what stochastic gradient descent will look like in, say, one epoch. So when I update the weights after every sample, it will kind of not really be a smooth fashion, because you will it basically just updates the weights after every sample, right? So there tends to be noise in between. So, and why this is commonly used is because this can help in regularization, and regularization is a topic that my friend Gandhar is going to explain in the next session. So we need more noise to help the machine learn better. In short, is what I'm saying. So stochastic gradient descent is quite widely used. So next we'll talk about mini batch gradient descent. So mini batch gradient descent basically takes the good qualities of both batch gradient descent and stochastic gradient descent. How it does that? You basically don't take one sample at a time, but you also don't consider all the samples at once. So what do you do in between? You just basically divide your data set into a set of smaller batches. And for each of those smaller batches, you will compute the gradient and you will change your variable after each of those iterations for those batches. So this is basically like a good in between of both batch gradient descent and stochastic gradient descent. But question arises, why do we do this? Like, why do we want to mix both of them when each of them are good in their own way? Because you end up having the good qualities of both batch gradient and stochastic gradient descent. So what are these good qualities? Batch gradient descent is it may have a longer processing time. So we don't want to really look at the entire data set and store the value for every sample, store the loss value for every sample. So one point I wanted to mention in batch gradient descent is that you basically just iterate exactly once, right? So it means you have to store the loss for each and every sample in some place. And after that, add up all those losses together and end up computing the final loss function. So the storage for all those samples may become, quite tedious if the data set is rather big. So we don't want batch gradient descent in big data sets. And we also take, good qualities of stochastic gradient descent because we basically kind of a good strike in between these two will give us batch gradient descent. So we also get to have noisy gradients from stochastic gradient descent, and that will help in regularization. So this is basically why mini batch gradient descent is good. So here you can see what exactly what the scientists have thought of when they thought of mini batch gradient descent. So it's a good combination between these two. So we spoke about gradient descent, but what exactly are the newer inventions in the pipeline? So we have newer optimizers called Adam and RMS prop that have been developed in the recent years, and these are actually good tweakings of the gradient descent formula. So why these tweakings are done is because, as I explained in question 2, or the question, if I try to help you recall, it's basically the question where you have many minimas, but you want to converge to the global minima. Why do we want to converge to the global minima? Because we want to minimize the loss function as much as possible. So in this scenario, we basically look at Adam and RMS prop. So these are two good newer inventions that have been invented to improve our gradient descent formula. So I'll just be going through your SGD with momentum here. So little bit of math may be involved in this. So I'll just kind of give you a gist of what this formula can help with. So this is basically a change in weight. I hope you guys can agree that when I say change in variable, it's basically your variable after the iteration is complete minus the variable before the iteration. So your change in variable is basically given by V of t, where V of t is the term providing velocity. So as the term suggests, SGD with momentum is a term that involves velocity to the variable. So when you have velocity, you tend to improve your speed. And when you have speed, you can escape smaller or say local minimas and go to the global one. So as you guys can see in the GIF, you basically have SGD with momentum in the purple color weight and gradient descent in the blue color weight. So when you have speed, it escaped the local minima and went to the global one. How does it get speed, or how does this tweaking the formula help it get speed? That I will kind of explain with this math over here. So you guys can see that this velocity at any point of time is basically beta which is a small number between 0 and 1, into velocity before the iteration, plus your learning rate into the gradient at that point. So if you guys try to compute, say, V of 1 is basically alpha into gradient at that point. V of 2 is basically beta into V of 1 plus alpha into gradient at the next point. So can you guys kind of see that V of 2 is basically beta into alpha of gradient 1 plus alpha into gradient 2. So in other words, this beta term helps to remember, or when I say remember, you basically in any point of time t, the formula has terms involving the gradient at time t equal to 0 also, say t equal to 1 also. So you basically remember the gradient for until that point of time t, and that basically improves your change in weight. When I say improves, the this velocity term is higher than what it would be without this beta term. So this velocity term is called the decayed sum of gradients. So your decayed sum of gradients helps to change this formula in such a way that you gain speed to the gradient descent formula. So this is something that's a good improvement. So we can see you get speed, and the sum of gradients basically accumulates when you keep on iterating over many points of time. So when something accumulates that much, the change in weight becomes something that's a very big value, and that helps it to get speed. So this is FGD with momentum. So there's also a problem with SGD with momentum also. So it may not be that it always kind of escapes a global minima. So we can kind of go through even better optimizers which have a short chance of getting a global minima. So we have SGD with momentum that it may also jump the global minima as well. So this is something we don't want. So some parts of the gradient descent formula have been changed so as to improve your uh, SGD with momentum also. So we have the next improvement, that is your root mean square propagation. So another word for this is RMS prop. So this is a quite a popular gradient descent formula. It sometimes turns out to be the best of all the optimizers in some cases and in some data sets. So what I spoke to you guys before. So if you guys see the formula of SGD with momentum, we can see that if I have a change in weight, or when I say change in weight, I mean velocity. So velocity is this term that equates to the change in weight. So when I have velocity equal to an expression that looks like this, it's called a decayed sum of gradients because you have a gradient term, and the terms keep on adding because of this beta factor, and you tend to remember a lot of past data. So it's called a decayed sum of gradients. So now we have a formula that looks like this. So now this formula is very similar to the previous formula except that you have gradient squared. So this V of t, I'm just defining it this way. So what V of t, if you compute it for larger values of time, you will find that it's basically the decayed sum of gradients squared. And what I do with this V of t, I basically put it in the denominator of your change in gradients. So we have change in gradients is equal to alpha, or your learning rate, into your gradient at that particular point of time divided by the decayed sum of gradients squared. Now, how does this help us? We have something in the denominator, so it may not be that it tends to make it faster, right? But you have a massive advantage of having the sum of gradients squared in the denominator. So let us try to visualize why that is the case. So I hope you guys kind of understood this. You have something like this. So V of 1 will basically be alpha into V of 0, and or gamma into V of 0, and V of 0 is basically uh, 1 minus gamma into gradient at time t equal to 0. So when you keep on computing V of t for larger values of time, you will find that it basically remembers gradient squared at t equal to 0, gradient squared at t equal to 1, gradient squared at t equal to 2, and so on and so forth until t minus 1. So you basically remember the values of gradient squared for all the values of t before your uh, before your time t. So now by having this in the denominator, why does it help? Now this is something I will kind of explain with a good diagram. So now we have a saddle point. So as many of you might have guessed, because I'm calling RMS prop as one of the best optimizers that have been invented in the past few decades. The white color weight kind of escapes the saddle point. So you have a saddle point, right? And what the saddle point is basically you have the direction of highest gradient at any point. It points towards the saddle point. So when your gradient points towards the saddle point, as I told you in the starting of the lecture, the gradient descent will basically just kind of go towards where the gradient is pointing it to. So in this case, the blue color ball is your normal gradient descent, and the white color ball is RMS prop. Now, how does RMS prop escape the saddle point? It's because of uh, this sum of gradient squared. So essentially, uh, RMS prop, it kind of it goes towards the saddle point initially, but then it sees that a large term that's having the gradient squared and goes towards the denominator of the formula. So as I told you guys, you have the denominator of the formula having the decay sum of gradient squared. So in this particular direction, that is basically a starting point to the saddle point. If the RMS prop keeps on going towards the saddle point, you will have a large term having, you know, all the gradients that is pointing towards the saddle point in the denominator. So it means what I'm basically trying to say is the change in weight that is related to this particular direction of gradient becomes very small. The reason it becomes very small is because you have in this particular direction, the sum of gradient squared keeps on accumulating in the denominator. When something becomes big in the denominator, it becomes smaller for the term overall. So in other words, the change in weight ends up becoming very small in this particular direction. Or in other words, the change in weight in other directions, it becomes high. So by other directions, it tends to stop moving towards this direction and tends to move in other directions. So it basically just escapes this saddle point and goes towards another global minima. So this will, I hope it's kind of clear to you guys. So this is how it is. So this is how RMS prop can escape saddle points easily. But what is the problem with RMS prop? I mean, we are talking like it's like really good, but like as I hope you guys can clearly see the problem with RMS prop, you have a very big term in the denominator. So obviously that means that the speed, or when I say the change in weight, it becomes really, it becomes really small. So we obviously need more speed to help with our computational efficiency. So what people thought of was to even improve this RMS prop even more by adding a speed term. So using that, you get this optimizer called Adam. So it is basically nothing but it takes the best of both momentum. So momentum I explained in the previous slide. So I think momentum is here. Yeah, you have momentum over here. So uh, just a sec. Yeah, you have momentum here. So what momentum does is it has the decayed sum of gradients, and I'll say sum of gradients because this formula basically remembers only the sum of gradients. So you'll have a gradient term in every term. So it has the decay sum of gradients. So and this is the decay sum of gradient squared. That is an RMS prop. So so I hope you guys can agree that m of t is nothing but the decay sum of gradients because it is a very similar formula with regard to momentum. So you have the decay sum of gradients and you also have the decay sum of gradient squared. So this we also saw in our previous RMS problem, the decay sum of gradient squared. So it's right here. The decay sum of gradient square is like this, and you have a you in fact have the same formula. So what it does is it just takes in the same formula of RMS prop and also multiplies the change in weight by your decay sum of gradients. So I hope you guys can see using this formula that I have I have my alpha and your decay sum of gradients divided by your decay sum of gradients squared. So I hope you guys can see from this formula that it's actually very similar to that of RMS prop. So here in RMS prop you have change in gradients is equal to alpha into gradient at that point of time divided by the decay sum of gradient squared. Whereas here we have the instead of gradient, I just replaced it with decay sum of gradients. So that gives it the speed. So I will say that in the end, Adam in general will have more speed than your RMS prop when it comes to converging. Reason being, I just have a decay sum of gradients in the numerator. So as and when you keep on increasing the time, so you have T1, T0, or no, or T0, T1, dot 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 till sometime T. So it will keep on accumulating in the numerator, and it will basically give its speed to the optimizer, or it will give speed to the weight. So this is Adam in short. So I'll be pictorially representing how Adam is after a short look at my coding because I tried to, yeah, we'll just be looking at a quick summary of whatever I've thought till now. So what did I speak about in this lecture? I spoke about stochastic gradient descent. I spoke about stochastic gradient descent with momentum. So that if you guys recall, it has the decay sum of gradients in the numerator. I I spoke about RMS prop and I also spoke about Adam. So an Adagrad is just another optimizer which is very similar to RMS prop. Like it's very similar, but RMS prop is more it's more used. So I did not cover Adagrad in this lecture. So as you guys can see, like I have this GIF loaded. Adam and RMS prop went very quickly and converged to the global minimum, followed by your SGD with momentum. So as you can see, a red color is Adam. So I just replayed it again. So here I just want to show you guys that RMS prop and Adam end up being the fastest out of all these optimizers because of their robustness. So all the formula I have explained before, and you have SGD with momentum taking the third place, and the other two uh, don't even kind of come near the global minima because there's a local minima right here. So Adam and RMS prop kind of escaped that local minima and went straight to the global one. So next I'll just kind of show you guys my I'll show you guys my notebook. So how the optimizers can compare with one another. So that will kind of help you kind of see why we use different optimizers. All right. So here what I did is I tried. So I will not be going over the data pre-processing because data pre-processing this has been more or less covered in previous lectures, and it will also be covered in today's lecture by my friend here, by my friend Gandhar here. So what is of interest in my lesson is we will be talking mostly about how different optimizers can compare. So neural networks was more or less a it was more or less taught in the previous lesson. So in previous sessions. So this is very I think fairly fine to understand, but that is not the agenda of my lesson here. So what in short what I did was I just created a neural network having two hidden layers for in the MNIST dataset. So and I will use I will use two different models in trying to have a good training for this data set. One of the models uses your gradient descent and the other model uses Adam. So I will just kind of go through this. So I told you guys I have two models. One of them uses gradient descent and the other uses Adam. So I use two models. So this sequential is something that creates a linear stack of layers. So as you can see my layers here. After this, I think this was covered in previous slides. So, but I will not be going over this in detail. However, I have added a summary for my model. So I will just explain what I've done using that summary. So you guys can see here, I've summarized my model in just this one cell. So what have I done? I have three layers, or this is my input layer. When I say dense is basically a term used to represent either a hidden layer or any neural network layer. So I have layer one, that is basically my input layer, activation function. So in this case, I have used ReLU activation for my input layer. Dropout is something that's going to be explained by either has explained in previous sessions or is going to be explained by my friend Gandhar in the next session. Dropout basically means you're going to drop drop few neurons in the neural network so as to improve computational efficiency. So I have a second layer here. So that's my hidden layer activated using my ReLU function. Again, use dropout. Finally, I have my output layer. And in the output layer, I have used a softmax activation. So basically, you guys can see 1, 2, 3. So I have 3 layers total. But now we come to the agenda of why I'm showing you this code. I have already gone through all the cells here. So let's see what the next cell does. Next cell, it compiled my model and I try to train my model based on this MNIST dataset using categorical cross entropy loss. Now this line is important. Optimizer is equal to SGD. So this is something that is basically specifying what optimizer you're going to use. So what I used is I just used my gradient descent optimizer. So SGD is basically stochastic gradient descent. And I try to compute the accuracy. What accuracy did I compute? You guys can see here. So I have just computed the accuracy after every epoch. So epoch 1 you have accuracy of 68. Then for total of 5 epochs, I have 68, 84, 87, 89, and 92. And in the test dataset, it had an accuracy